Hello, everyone, and thank you for listening to this presentation. My name is Yerro, and the co-authors of this work are John Murphy and Kenichi Soga. Internal erosion is the mobilization of particles in a soil mass as a result of seepage. This phenomenon is a critical geotechnical hazard because it affects the stability of water retention structures, being one of the leading causes of failures in levees and earth dams. However, the numerical study of internal erosion is challenging. This is because despite the initiation and progression of this mechanism depends on particle-to-particle interactions and can be considered a microscale process, its consequences can trigger large deformations and have large impacts. One example is the global failure of the Teton Dam in 1976, the one that is presented in this picture. So it's challenging to find a unique framework that can simulate both everything together. So the overarching goal of this ongoing research is precisely this one, so to propose a numerical framework to study the overall initiation, progression, and consequences of internal erosion. And in particular, for this presentation, I will compare the two recent MPM formulations that have been proposed for the simulation of internal erosion processes. So considering a continuum-based approach, the process of internal erosion can be understood as a two-phase mechanism that accounts for mass exchange between solid and liquid phases. This sketch represents the evolution of a phase diagram during seepage, assuming that we have a saturated bimodal soil. These ends basically represent the volumetric concentration ratio of the phases and the components of these phases. And in particular, we have that the solid phase consists of two different parts. One is basically the solid skeleton or the non-erodible solid part, which is generally the coarse fraction, and then some fines that are susceptible to erosion. So at certain conditions of seepage conditions, we can eventually have the full, all these fines washed out from the system. In this work, we are using the material point method for the simulation of internal erosion. This is a method that can deal with large deformations and that uses a set of integration points that are called material points to carry all the information of the continuum, and then they can move through this continuum, through this computational mesh, background computational mesh. With this framework, we can simulate history-dependent materials, and in the last 10 years or so, there have been different coupled hydromechanical formulations available. If we want to account for the mass transfer between different phases, the most important, one of the most important governing equations that we need to add into the system is the erosion law, which is evaluated at the material points. This connects the microscale nature of the internal erosion mechanism with a large-scale viewpoint of the continuum-based MPM framework. In MPM, there are two ways to simulate saturated media or hydromechanical interactions. The first one is if we can use a single point approach in which every single material point carries information from both solid phase and liquid phase. Material points actually move together with a solid skeleton, with a solid phase, and the liquid is described within these points relative to the solid. In this presentation, I will use the extension of this formulation to account for mass transfer from the solid phase to the liquid phase. Then the second MPM approach to account for hydromechanical interactions is the double point approach, where we use two sets of material points. One set represents just the dry or the solid part, the solid phase of the problem, and then the second set that represents the liquid phase. So in the liquid, we can have free water or porous water, and for the solid phase, we can have like just dry soil, or if it's part of this saturated soil. So the saturated media is accounted at the element level when we have the two continuum or the two particles sharing the same cell. It's important to identify that the two phases here are represented individually by the two sets of material points. In this presentation also, I'm using this recent advancement on this formulation that accounts for mass exchange from solid phase to the liquid phase. One important aspect on the double point approach is that when we evaluate the erosion law, This erosion law is evaluated only at the solid material points. Contrary to the single point approach where all material points carry all the information, in this, the double point approach, the solid material points only carry information from the solid. However, the erosion law, which is presented here very generally in this equation, can depend on some properties or variables that are stored only in the liquid material point. So we need some transfer of information from the liquid material points to the solid material points. And this process is represented very schematically here. So initially we have these two sets of material points in an element, which represents this porous media, saturated porous media. Then those variables that are only stored at the liquid material points that are necessary to evaluate the erosion law are evaluated at the center of the element. And then with this information, we can evaluate at the solid material points the erosion law, considering these element variables. Then we can evaluate what is the actual mass eroded per each solid material point, and then this mass is distributed among the liquid material points that are currently in that cell. So in the end, we can have this mass transfer from the solid material points to the liquid material points. In this presentation, we wanted just to validate this formulation using a theoretical problem with analytical solution. So we are considering what we call suffusion process, which is internal erosion when the solid skeleton basically is not mobilized. So in these results, we assume that the solid material points are fixed or they don't accumulate any deformation. In particular, we account for one-dimensional vertical flow, downward flow, and we prescribe the boundary conditions slightly different in the two approaches. On the left-hand side, we prescribe, for the single point formulation, we prescribe the velocity of the flow using this pressure gradient at the top and bottom boundaries. Both lateral boundaries are impervious. On the right-hand side, you have the exact same erodible soil specimen represented in pink or red, and then on top of that, you have these inflow elements that add liquid material points at a certain rate. So we basically impose the vertical velocity at these liquid material points in order to induce the same flow rate as in the one on the left-hand side. So both models are slightly different, but we represent the exact same mechanism. So at the bottom of on this table, you have the summary of the material parameters that we consider. Most importantly, I want to emphasize that the initial porosity is 0.3, and the initial concentration ratio of fine grains in both samples is 0.1, which means that the maximum porosity that we could expect in case everything is washed out is 0.4. The results are presented here for two different simple erosion laws. One is the constant erosion law that depends on alpha, and the non-constant erosion law that depends also on a factor beta and the current porosity of the sample and the maximum porosity. So here are the results presented: evolution of porosity with time that goes from 0.3 to eventually 0.4. And we see that the results for the double and the single point formulation converge to the analytical solution. Here on the right-hand side, you also see the evolution of solid mass and liquid mass for all the cases. And if you sum up both of them, you get the total mass, and this remains constant, which is consistent. I also want to highlight one particularity of the double point formulation is that, well, if you look at this plot, we have the analytical solution, which over here, and then three different simulations using the double point formulation, considering different liquid material points from the beginning. If you have one liquid material point per element in the beginning, you get these results, which they do not resemble, or they do not convert the analytical solution. However, if you increase the number of liquid material points in the system, then the solution converges to the analytical one. The reason for that is because if you use just too few liquid material points in the system, eventually in the eroded or in the wherever you expect to have this saturated material, you may have eventually one element or a few elements that become empty of liquid material points, and then the code understands those elements as just dry soil, and erosion cannot develop in those elements for that particular time step. Therefore, what happens in the end is that we underestimate the erosion, accumulated erosion in the sample. So it's very important to do this sensitivity analysis in the beginning, just to make sure that you have enough liquid material points in the system. As a conclusion, or to end this presentation, I presented the material point method, which shows promise on modeling internal erosion mechanisms using these extended formulations. We presented both single point and double point formulations very briefly, and we validated our results using 1D theoretical erosion tests. For future work, we have to keep further validating the formulations for more complicated scenarios and coupling with solid skeleton deformation. You also want to couple this behavior with changes in porosity, such as in hydraulic conductivity and stress-strain relationships. We want to include the position law as well. We can do that, similar to the erosion law. And then for computational purposes, we will have to consider some implicit time discretization skip to optimize the computational time. Finally, I want to highlight that this work has been done in the framework of the ENURE-3D NPM research community. ENURE-3D is a software that is open source. We are working on right now on an in-house version of this ENURE-3D, but eventually, probably all this development will be in the open source version. So thank you for your attention, and I hope you enjoyed. If you have any question, please let me know.